This is the modern periodic table. This is a table of everything. Everything that is matter, everything that has a mass, is made out of the elements. We are also made out of these elements. They have existed long before our own existence, only a few of them are human-made. There is a great deal of information in this single image, very close to the literal sense of a saying, a picture is worth 1,000 words. The image may look a bit boring, or difficult to make sense of, but it actually is very interesting and not that difficult to understand. Besides that, basics of some other aspects of matter will be introduced, because they possess the answers to many why and how questions. After having learned those aspects, one would be able to comprehend and appreciate the periodic table better. In this age of information, probably all of us know or have heard that everything is composed of atoms that contain electrons, protons and neutrons. If you have studied middle school science, you would know that electrons revolve around nucleus. You have probably also heard a cliché that atoms are to everything as bricks are to a wall. However, many of us do not know why everything is made of atoms and what forces are holding the components of atom together. Turns out, there are natural forces that control everything. There are 4 known fundamental forces in universe. First one is the gravity or gravitational force. Gravity is a force of attraction discovered by Isaac Newton, probably the greatest mind in the recorded history of humankind. He discovered that anything that has a mass attracts another mass. Newton also formulated gravitational force given as F equals G, m1, m2, divided by I squared, where m1 and m2 are masses, r is the distance between them, and G is a constant of proportionality, meaning to what proportion the gravity will change if the masses and the distance between them are changed. Thus, gravity depends on how big the masses are and how distant they are from each other. If masses are too small, the gravity will be negligible, but if at least one mass is big, gravity will be observable. For example, gravity between Margot Robbie and I is negligible, but the gravity between an apple and Earth, Earth and Sun, and Moon and Earth can be observed. Here, we can see there is a gravity between Sun and Earth, but the combination of their masses and the distance between them only allows the Earth to revolve around the Sun in a fixed orbit. Similarly, Moon and Earth have gravity between them, their masses and distance only allow the Moon to revolve around Earth. The second fundamental force is electromagnetic force. This force has 2 components, electrostatic and magnetic. This force acts only on charged bodies. If body is charged, there will be electrostatic force present. If charged body is in motion, besides electrostatic, the magnetic component of force will also be in action. Matter is either positively charged or negatively charged or not charged at all. Charge, by the way, is a fundamental property of matter. The smallest unit of charge is the charge on an electron. The bodies with like charges repel each other, whereas the oppositely charged bodies will attract each other. The electrostatic force has the same expression as gravitational force as, instead of masses, charges are taken into account, and C is a constant of proportionality called Coulomb. This equation can also be written in terms of electrons and protons. The greater the distance between electrons and protons, the lesser the electrostatic force and vice versa. Third force is called strong nuclear force. Like gravity, this is also only a force of attraction, but it works only at very short distances. This force is effective on bodies that are within the range of 10 to the power minus 15 meters. This distance is 100,000 times smaller than the size of an atom. However, this force is very strong, much stronger than gravity and the electromagnetic force. This strong force is responsible for keeping the subatomic particles like protons and neutrons together in the nucleus. Protons in the nucleus are positively charged, which should repel each other due to electrostatic force, but strong nuclear force is so strong that it overcomes the electrostatic repulsive force. The strong nuclear force does not care about the charge or the mass. It simply makes masses attract each other when they are within the range of 10 to the power minus 15 meters. The last known fundamental force of universe is the weak nuclear force. This force also works at very short distances, even 100 times shorter than strong nuclear force works at. Weak nuclear force is effective only at 10 to power minus 17 meters. Things that are held together by this force sometimes simply break apart because this force, as name suggests, is very weak. For example, a carbon-11 atom will decay into boron-11 with the release of some other particle. However, the weak nuclear force is also responsible for bringing things together. The fusion reaction of two hydrogen atoms combining to form a helium atom is because of this weak attractive force. This fusion reaction is continuously taking place in Sun and many other stars. The atmosphere in Sun provides all the required conditions of this fusion reaction. There is high temperature, high pressure, and short distances due to high concentration that make fusion reaction possible. These were the four fundamental forces of universe. Easy way to remember these forces is to connect them with their key factors. For example, gravity depends on masses. Electromagnetic force depends on positive and negative charges. Strong nuclear force works at distances within 10 to power minus 15 meters, and weak nuclear force works at distance within 10 to power minus 17 meters. After a small account on the fundamental forces of nature, the other aspect of matter, the energy, is needed to be discussed. For the relation between mass and energy, here's the world's most famous equation, Einstein's mass-energy convertibility equation, given as E is equal to mc squared, where c is the speed of light, equal to 300 million meters per second. This equation means that mass can be converted to energy if it moves with the speed of light, or energy can be converted to mass, meaning the energy and mass are directly proportional to each other with a constant of proportionality equal to the speed of light. It was important to introduce this equation because this would be useful to know the origin of matter, the beginning of everything. In the beginning, there was nothing, then all of a sudden, a teeny tiny dot of light started to appear, or somebody commanded, "Let there be light."
Or ho ja, or tathastu.
Or something similar, whatever you believe in is right. This tiny dot that is so dense in energy that all the matter and energy present today in universe came out from this dot. This dot was extremely hot and dense. Then, suddenly, it started to expand with high speed. This expansion led to high and low density regions and less and more hot regions. Subsequently, there is a big explosion, extremely fast, extremely hot. All heat and other energy waves are expanding rapidly. By time, the expansion led to decrease in heat. Then the energy started to convert to matter at unitary levels. The very first matter that came into existence is electrons, then quarks. However, these tiny particles are still very hot and moving too fast to combine with anything. As some more time passes, the fusion of tiny quarks led to the formation of protons and neutrons. With the passage of more time, things got less hot and calmer, the electrons and protons got a chance to interact with each other. This resulted in the formation of the first element called hydrogen. Yes, hydrogen is an element without neutron. Many other reactions started to take place spontaneously. Sometimes neutron combined with a hydrogen atom to form deuterium. Deuterium is an isotope of hydrogen with a neutron in its nucleus. Isotopes of an element are different from each other only by their number of neutrons. The fusion of two deuterium atoms led to the formation of helium atom. Besides the formation of helium atom, three forces of nature can also be seen in action here. The strong nuclear force keeps protons and neutrons together in the nucleus. The electrostatic force making the negative electron revolves around the nucleus in a fixed orbit. The fusion reaction itself is the evidence of the presence of the weak nuclear force. Given all the conditions of extremely high temperature and high pressure, many fusions occurred. Some resulted in the formation of helium atoms, sometimes the hydrogen atoms fused with helium to form lithium atoms. and the fusion of hydrogen and lithium led to the formation of beryllium. Similarly, boron, carbon and many other elements formed. Before going any further, it is good time to understand some conventional ways of writing atoms as their symbols and in terms of their electrons, protons and neutrons. You might have noticed that elements are frequently written as their symbols. One should learn the symbolic representation of atoms to make one's life easier. Sodium's symbol is Na. On the top left corner of the symbol, mass number or atomic mass is written. Mass number is the sum of number of neutrons and protons present in an atom. At the left bottom side, atomic number or the number of protons is written. At right bottom side, number of atoms is written. If there is only one atom, usually nothing is written, because one is already represented by the symbol. At the top right corner, charge on atom is written, which depends on the gain or loss of electrons. Some examples of elements written with their mass numbers are carbon 11, carbon 12, carbon 13, carbon 14, nitrogen 14, boron 11 and hydrogen. The fusion reactions for the formation of elements can also be expressed as a combination of electrons, protons and neutrons. For example, lithium and hydrogen combine to form beryllium. This can be expressed as the combination of 4 electrons, 4 protons and 5 neutrons. Similarly, 5 electrons, 5 protons and 5 neutrons combine to form boron. 6 electrons, 6 protons and 6 neutrons combine to form carbon atom. Like the isotope of hydrogen, isotopes of other elements were formed as well. If 6 electrons, 6 protons and 7 neutrons combine, the resulting atom will be carbon 13, which is an isotope of carbon. If 6 electrons, 6 protons and 8 neutrons combine, it will result in the formation of carbon 14, and if 7 electrons, 7 protons and 7 neutrons combine, the resulting atom will be nitrogen 14. Similarly, the elements with higher number of electrons, protons and neutrons were formed. It is estimated that the formation of more heavy elements like iron, silver and gold required other kinds of cosmic explosions that would have provided the desired conditions of such fusions. Some necessary cosmic events from the beginning have been summarized. One should get a sensible idea about how several elements and their isotopes were formed. Hopefully this table looks little more interesting now. However, the representation of all the known elements was not always like this. Let's briefly learn about how the modern periodic table came into its shape. De Bruijn's triads is probably the earliest attempt to organize elements based on their mass numbers. Triad, meaning a group of 3. In 1824, de Bruijn proposed that elements with similar properties can be arranged into groups of 3. In this arrangement, the mass number of the middle element is roughly the average of the mass numbers of first and last element. For example, lithium, sodium and potassium form one triad. The average of lithium and potassium's mass numbers is the mass number of sodium. Same idea applies on calcium, strontium and barium triad. And some other triads. It was roughly true, but false for other triads like fluorine, chlorine and bromine. And there were many elements yet to be discovered. There are several contributors to the modern periodic table, but only the major ones will be talked about today. The first one is Dmitri Mendeleev. In 1907, Mendeleev came up with his periodic law, which states that the elements should be arranged based on their atomic masses. He was the first one to represent the elements in the table by their symbols and assign each element its own position in the table. At this time, many more elements had been discovered. With this arrangement, Mendeleev also predicted the properties of elements which had not been discovered yet. He also predicted the exact positions of these elements in its table. Within the next 20 years, his predictions came out to be true. How cool is that? Mendeleev's periodic table is universally appreciated even today, but it was not perfect. Then Henry Moseley in 1913 proposed his periodic law, which states that the elements should be arranged according to their atomic numbers, meaning the number of protons. He found that the square root of X-ray frequencies of elements, which are unique to each element, are directly proportional to the atomic numbers of elements. This solved the isotope problem in Mendeleev's periodic table. Based on atomic masses, carbon-14 and nitrogen-14 should be located in same position, but Moseley's law allowed them the correct positions. The modern periodic table follows Moseley's law, meaning that the elements in the modern periodic table are arranged according to their atomic numbers. All the rows and columns in the table are filled with elements. It is all completed. Unless someday period 8 or greater element is discovered or synthesized. We never know. Anyway, here's a simplified version of the modern periodic table, less informative, but easier to read. Most of the elements in the table are metals, which are starting from left of the table. The far right part belongs to nonmetals. There is a diagonal separation between metals and nonmetals by the elements classified as metalloids, as they exhibit the properties of both metals and nonmetals. There are 18 columns which are called groups and 7 rows which are called periods. Lanthanides and actinides are part of 6th and 7th periods. Groups in the table also have their conventional names. First group elements are called alkali metals. Second group elements are called alkaline earth metals. The elements from group 3 to group 12 are collectively called transition metals. Group 17 elements are called halogens, and, at last but not the least, group 18 elements are called noble gases. Period-wise, it can be seen that with every preceding element, there is an increase of a proton count, which is also equal to an electron count. As the period ends, a new period and a new electronic shell starts. Mind you that electronic shell, orbit or energy levels are the same things. So, after the period ends, a new period and a new shell starts. The shell keeps accommodating electrons until it is completely filled, then the same process repeats. Thus, the number of elements in each period is equal to the capacity of the shell to accommodate electrons. Another point to be concluded here is that the number of period from which an element belongs to is equal to the number of shells that element has. For example, hydrogen and helium belong to the period 1, they each will have only one shell. And as there are only 2 elements in period 1, the elements in this period can have maximum of 2 electrons. The period 2 has 8 elements, therefore, each element of this period will have 2 shells and the capacity of 8 electrons. Generally, the same idea applies on the periods. After period 3, the electronic capacity keeps on increasing as 14, 18, and 22. The starting new shell also indicates the noble nature of the group 18 elements because they have achieved electronic stability by completing the electronic shell. The achievement of electronic stability is crucial because that's the root of unique properties of each element. Everything in nature wants to be stable or be in a state of equilibrium with its surroundings. Atoms achieve stability by completing their outermost electronic shells. Atoms can have a completely filled outermost shell either by losing or by gaining electrons. For lithium, it is easier to lose 1 electron and have outermost shell completed than to gain 7 electrons. By losing electron, atom gets a positive charge and is called a positive ion or a cation. For fluorine, it is easier to gain 1 electron and complete its outermost shell than to lose 7 electrons. By gaining electron, an atom gets a negative charge and is called a negative ion or anion. Hydrogen has ability to either gain an electron and form a hydride ion or lose an electron and hang out freely as a proton. At this point, one should be able to know the nature of the element just by knowing its atomic number or the position in the periodic table. Let's see what property trends of elements could be predicted after having learned the periodicity and the desire to achieve electronic stability driven by the electrostatic force. The first thing is metallic character. Most of the elements are metals. What makes elements metals depends on how they achieve electronic stability. The elements that can give off their electrons are metals, and the elements that would gain electrons to achieve stability are nonmetals. The trend it follows is that the metallic character increases down the group and decreases from left to right along the period. The metallic character changes from metallic to non-metallic at the diagonal borderline of metalloids. Second thing is the atomic size. Atoms are very small in size. They are about 10 billion times smaller than a meter. Therefore, they cannot be measured directly. The size of an atom is measured by measuring radii of 2 closely packed atoms of the same element. That would give the diameter of the atom. Trend-wise, the atomic size increases going down a group as number of shells increases with every preceding period. The atomic size decreases from left to right. The number of shells remains the same, but increasing number of protons increases nuclear pull on the electrons. This causes a shrinking size effect on atom. While talking about the atomic size, it would be helpful to discuss the ionic size of the elements. The size of a cation till the metallic area of the table follows the same trend as does the neutral atom, that is, it increases down the group whereas it decreases right till metalloids. The size of a cation compared to its corresponding neutral atom will definitely be smaller. That is, because there is a decrease of a shell and an increase in the nuclear pull. In case of anions, the size increases down the group, but increases along the period after metalloids because one or more electrons have been added. This could add a new shell or just cause electrons to expand in space due to interelectronic repulsion. For the same reasons, the size of an anion will be greater than its corresponding neutral atom. Another property to be discussed is the ionization energy. When an atom loses an electron, there is a release of energy called ionization energy. The ionization energy decreases when moving top to bottom in the periodic table due to the increasing distance between nucleus and the outermost shell. For example, the outermost electron in sodium is farther from nucleus compared to outermost electron of lithium. Across the period, it increases from left to right because of greater nuclear pull. For group 2 or higher group elements, there will be first ionization energy as well as second ionization energy and so on. The first ionization energy will be smaller than second ionization energy and second will be smaller than third. This is because every time an electron is removed, nuclear pull on the rest of the electrons gets stronger. The electron affinity also follows a trend in the table. Electron affinity is the energy absorbed or released when an atom gains an electron. Electron affinity decreases down the group because of lesser nuclear pull on the distant electrons. Therefore, the lesser energy is needed to add an electron in an atom. Generally, it increases along a period, because moving right, only fewer and fewer electrons are needed to complete the outermost shell, thus it becomes easier to add an electron in the atoms belonging to right side of the table. In case of oxygen, when an electron is added to oxygen, the energy is released. When a second electron is added to oxygen anion, there is repulsion towards the incoming electron, thus energy is absorbed in this process. After electron affinity, electronegativity of a substance will be described. Electronegativity is the tendency of an atom or molecule to attract electrons. Trend-wise, it decreases down the group and increases from left to right along the period. One can predict that, excluding the noble gases, fluorine would be the most electronegative atom on periodic table. It will have the strongest nuclear pull because, for having only 2 shells, it has the greatest number of protons. Moving from left to right, electronegativity keeps increasing. Carbon is less electronegative than nitrogen, nitrogen is less electronegative than oxygen, and oxygen is less electronegative than fluorine. Group-wise, fluorine is more electronegative than chlorine, chlorine is more electronegative than bromine, and so on. This knowledge helps a lot in organic chemistry. Electronegativity is basically another name for nuclear pull. It is measured by different scales. According to the Pauling scale, the electronegativity of fluorine is about 4.0. The last property trend in this presentation is the phase change, or simply the melting and boiling points. The melting and boiling points of elements generally decreases down the group and increases across the period. But this happens till carbon. After that, the melting points decrease abruptly. This happens because of the different type of bonding is involved. Carbon in group 14 has 4 electrons in its outermost shell. It can gain 4 electrons or lose 4 electrons, but it rather forms a different kind of bond, a shared electrons bond, called the covalent bond. That's why diamond, the crystallized carbon, has a very high melting point. So far, one should have learned about the fundamental forces of nature and their role in the formation of the elements. The periodic table and the trends of properties of the elements in the table. The description of the atom and its components. The electrons revolve around the nucleus in fixed shells or orbits. First shell can have maximum of 2 electrons, second and third can have 8 in each, and so on. There is one last thing, probably should be talked about. That is the block classification of the elements of the periodic table. The block classification is based on SPD and F orbitals. Orbitals are the spaces within a shell where electrons actually reside. All 4 orbitals have particular shapes. S orbitals are spherical, P orbitals are dumbbell-shaped, and the shapes of D and F orbitals are a little too complicated to be explained at this level. Just to give an idea, the orbital shapes are obtained by plotting 3D graphs of mathematical equations that represent regions in atomic space. The orbitals are of different energy levels within the shells. S orbital is at the lowest level and F orbital is at the highest energy level. First shells have only S kind of orbitals. Higher shells have more or all 4 kinds of orbitals. More accurate models of carbon and helium atoms should look like these. Carbon's first shell has only S orbital, which accommodates 2 electrons. Rest of the 4 electrons will be accommodated by second shell and its S and P orbitals. 2 of the 4 will reside in 2s, meaning S orbital in second shell, and remaining 2 electrons will reside in P orbitals. In case of helium, there is only 1 shell that has only S orbital. Therefore, both electrons of helium reside in one S orbital. The elemental blocks are classified on the basis of the highest orbital accommodating electrons. This makes helium an S block element. Carbon's outermost electrons reside in S and P orbitals, but P is higher orbital, thus carbon is a P block element. Same idea applies on D and F block elements. The block classification of elements is shown by simply labeling the groups and selection of periods in the table as shown here. Today's presentation was an attempt to deliver basic concepts of physical science in a way that students or laymen can understand easily. If the viewer can remember a few things, please remember the following lines. There are forces in nature that control everything. Everything in nature wants to be stable or be in a state of equilibrium with its surroundings. Electrostatic force controls interactions of electrons and nucleus. Thanks for your time. Kindly let me know whether you learned or not.